Today I'm going to talk to you, I'm going to basically give you an introduction to volcanism in Big Bend National Park. There'll be a locator map here in a moment, but I assume that many of you know where Big Bend is at. It's over in the western part of the state. And today we're going to focus on the Mafic volcanism. I brought a couple of samples with me that will allow you to come up and take a look at maybe later on or after the talk and ask questions about. One of which is from Big Bend National Park, and the other of which is from a place called Kilbourne Hole, which is just over the border in New Mexico, and that's an actual piece of the mantle. So I'll be talking about the mantle today, and I brought a piece of the mantle with me. I didn't go down to the mantle to get it, but I do have a piece of the mantle. So before I get going too far, I'll let you mention this to you. This sample is from Big Bend National Park, and you're not allowed to take rocks from the park. Okay, we had a special collection permit, and so all the samples that we have to be archived and then eventually stored at the Smithsonian Institute when we're finished with them. So don't go to the park and take rocks. We got stopped 3 times by the park police while we were there, and one of them was not very pleasant. But they read our permit over and over and over again, and we're ready. You know, they'll throw you out of the park if you take rocks. So unless you have a permit, and like many things governmental, to get a permit is a little bit of paperwork. So, but we can talk about that a little bit as well. So, Big Bend National Park, it's a really neat place. How many people have been there? Well, quite a good number of you. Looks like almost 10 or so. That's cool. Well, if you get the chance, I highly recommend it. Don't go in the summer; it's hot. All right, but go over spring break or something some year. The weather can be quite pleasant. So, it covers about 800,000 acres, which is large for a lot of places. This is almost the exact same size as Rhode Island. So this is one of those Rhode Island comparisons that everybody likes to use. So it's almost the exact same size as Rhode Island. They get about 1/3 of a million tourists every year. Go in the wintertime. It can be quite nice. There's a lot of extrusive and intrusive igneous rocks there. And there's elevations that get up to 8,000 feet above sea level. So many folks that go there from the coastal plain are huffing and puffing to get up these hills because these hills are quite high elevation. A lot of folks go there to look at the different birds and plants, which is pretty cool too. There's also mineral deposits around Big Bend National Park. There's some mercury deposits and uranium deposits and some fluorine deposits. Most of the fluorine that I'm familiar with are just across the border in Mexico, but there may be some in the United States as well. And all 3 of these types of mineral deposits are related to the volcanism that occurred there. Okay, so just a couple of facts of why Big Bend's pretty cool. The other reason why Big Bend is so cool is that we've got great exposure of really awesome volcanic and plutonic rocks. Okay, and so this is called Crown Mountain, and we can see these massive exposures. The height on this, you know, there's no human for scale. If there was, you would barely be able to see them right there. So the relief on this is probably getting close to 1,000 feet. So this is a big area with a lot of up and a lot of rock and a lot of cactus. But it's a pretty cool area, and I would encourage you all to get out there if you can sometime. All right. So this is a very abbreviated geologic history of the Big Bend area. We can go back in time to the Marathon Orogeny. I think some of you that have worked in geosciences around here have heard of the Marathon Orogeny. Orogeny is a time of mountain building, okay? And the Marathon Orogeny actually occurred when the United States and Europe were coming together during a plate tectonic cycle, all right? So this Marathon Orogeny is actually related to the Appalachian Mountain Formation, okay? Starting back about 350 million years ago. So it's interesting that you go down the Appalachian Mountains in the United States all the way across to the Ouachitas over there in Oklahoma, and then down to the Marathon area just north of Big Bend. All those areas were experiencing mountain building at about the same time with the collision of North America and Europe. All right. In the late Triassic time, we started to rift apart North America and South America and North America and Europe. Okay. The breakup of Pangaea. All right. And that's when we started to form the Gulf of Mexico. This is when we started to form a lot of these platform limestone deposits. Some of you that may have been in geology might be studying some of these limestones or other platform style deposits. We then had another orogeny, another form of mountain building during the Laramide. All right, and this happened maybe around 70 to 50 million years ago. This happened due to compression. This is what formed a lot of the Rocky Mountain areas. Okay, so we had compression pushing together to form plates, buckle the plates and form mountains. Finally, well, not finally, now after that orogeny, after the laramide, is when we started to get this volcanism that makes up these awesome exposures like Crown Mountain. Okay? So from about 46 to 28 million years ago is when we have these large, some of these eruptions are huge, eruptions that really started to dominate the landscape in Big Bend. These eruptions were so large that they've dropped ash all the way out into the Gulf of Mexico from Big Bend. Okay? So to put it another way, they might not quite be Yellowstone-sized eruptions, but they were of that scale. They were very, very, very large eruptions that happened, a lot of them around 30 million years ago. And then more recently, from 25 to about 2 million years ago, we've had Basin and Range extensional faulting. So this area is almost like an accordion. First we crammed it together, then we pulled it apart, then we crammed it together, then we pulled it apart. And so there's one more piece that we'll add to this. If we go way back in time, this is on this next slide here, way back in the Neoproterozoic, around 700 million years ago, we actually had our first original rifting of North America. Okay? How many have heard of the supercontinent Gondwanaland? Just a few of you. Well, there was a supercontinent before Pangaea that was called Gondwanaland. Okay? And the western part of Texas was actually abutted against probably Antarctica. Okay? That's pretty cool. I mean, we all know where Antarctica is. It's a long ways away now. But back about 700 million years ago, there was a mountain building episode, and then the Earth rifted apart. Well, when the Earth rifted apart, or especially North America, 700 million years ago, it actually left a scar deep within the Earth. Okay? And that is still controlling some of the geology that we see over in Big Bend National Park. So the rest of this is a rundown of what I've just talked about, but I wanted to add this one piece that happened first. There's no evidence on the surface of this anymore out there, but it's probably one of the things that's helping to control some of the geology we see, even though it happened 700 million years ago. So this here's the simple little diagram showing us the Appalachian Mountains here, the Ouachita Mountains over here in Oklahoma, and the same mountain building episode that happened to form the Appalachians also formed the Marathon Mountains just north of Big Bend. The same types of activities were going on in the Big Bend area too. We just don't see them anymore because we've covered them with younger rocks. Okay? So our focus in this talk today is going to be the generation of magmas, and specifically we're going to talk about the generation of mafic magmas. So mafic magmas are magmas like basalt, okay? Things that are high in iron and magnesium, low in silica. And the reason that we care about the generation of mafic magmas is because mafic magma generation drives all other volcanism. All right? Well, drives almost all other volcanism. We'll put it almost in there. Okay? So we have to understand how we're generating these mafic magmas before we can generate other more explosive magmas, like rhyolitic magmas or things like you might see in an explosive volcano. So here's the great state of Texas. Here we are down here in Corpus Christi. Kingsville's right there. Big Bend is over here. And it's a fairly short drive to get there. It's about 9.5, 10 hours to get there. So it's not too far away. Especially if you want to go visit some reasonably young volcanoes, 30 million years old or so. A lot closer than going all the way to the Pacific Northwest, where it's going to be raining. So as we can see, we've got a lot of sedimentary rocks that line up across here. Here's the Llano uplift, so these are some nice granites, which I would highly encourage you to go visit at some point too. Okay? But over here we get to these igneous rocks and these red colors over here in the Big Bend area. So we'll focus in on those a little bit. And this is focusing in on Big Bend National Park. Remember, this is the size of Rhode Island. All right? You can go to Rhode Island and study geology and not move 25 miles away from your campus. This whole thing is the size of Rhode Island. And there's an enormous amount of geology to do there. We've got some of these Cretaceous carbonate sediments over here, but the ones that we're most interested in are going to be the volcanic rocks and some of these plutons here. That's the Ward Mountain pluton. You see this dotted green line here with a PC in the center of it? Okay, that's the Pine Canyon caldera. That's a giant caldera forming eruption happened there about 29 million years ago. Left a scar in the earth. It's about probably about 6 kilometers by about 8 kilometers, okay? And that's an eruption that would be not quite on the order of Yellowstone, but getting close to Yellowstone size eruptions. If those that have looked into the Yellowstone supereruption. Have you heard of that? Some of you have heard of the Yellowstone supereruptions. All right. So getting pretty close to that size. And that happened right from that spot right there. So this is the area we're going to be focusing on. And we're going to primarily today be looking at the mafic magmas so that we can better understand how they were generated and what they might, how they might produce other magmas. So in my bag I brought the geologic map of the Chisos Mountains, which are largely made up of volcanics. That was produced in 2011. And I put this up here to illustrate one of the reasons why I'm really excited about going to Big Bend to do some work. One of the reasons I'm excited about going to Big Bend is because this guy in his 2011 paper said source of this tuff, which is a type of volcanic rock, is not known. The volcano Dominguez Mountain has not been studied in any detail. Source of these flows is not known. The sandstone source, and he's talking about a tuffaceous source, so a sandstone that came directly basically from the weathering products of a volcano, is of unknown derivation. Don't know where it came from. The trachyte flows source is unknown. Altered parts of the War Mountain Pluton have not been studied. Dominguez Mountain basalt's age and composition not known. Maybe Oligocene, who knows? Okay, and on and on and on and on. I could list 3 pages of this type of stuff from this very recent publication. So there's a lot of geology there, and it hasn't been investigated very carefully, which is kind of strange because it's in a national park. You'd think it'd be easy to get to. Hard to get samples. It's easy to go visit, but hard to take samples. All right. So that's one of the cool reasons why Big Bend is a neat place to do some research, and it's close enough that you can actually go there. Okay, you don't have to fly to South America or some faraway place to look at some really awesome, igneous rocks. So basalt, as I mentioned to you, that's the driver of magmatism. Okay, that's going to be the focus of today's talk. And we're going to talk about 2 different flavors of basalt, 2 ways in which we can make slightly different basalts, and they're going to actually control all the magmatism that we see. All right. We also have the 3 classifications of rock. For those of you that have taken probably a physical geology class, know you've got basaltic rocks or mafic rocks, intermediate rocks, and then rhyolites or silicic rocks. And this diagram here is called a TAS, which stands for total alkalis, sodium and potassium, versus silica. Okay? And so if we plot the total alkalis, or sodium plus potassium versus silica, we have this field down here that's labeled basalt for volcanic rocks. And we got these intermediate rocks that are called things like basaltic andesite, andesite, and dacite. Then we got these rocks that are called rhyolite. These would be your silicic rocks or your high silica rocks. All right. We also have a few other fields on here that's got these weird names called like trachydacite and trachybasalts. We're going to actually talk a little bit about these trachy rocks. Okay. Some of you may not have heard this term before, and they're actually very, very common in the Big Bend area, and there's a reason for that. All right. So today we're primarily going to talk about basalts. If we were to continue on, we could talk about how the rhyolites, which make up much of the park as well, are made, and that's either through fractional crystallization, okay, where we remove crystals. We'll see how that process works today. Right. We can have small degrees of partial melting in the crust. This is what I actually spent much of my Ph.D. working on. Or we can have these things that are called continuous RAFC processes. This is just a big fancy term for saying that we have a lot of recharge assimilation and fractional crystallization. So we've got a magma, we're adding stuff to it, we're removing things from it, and if you add stuff to a magma and remove other things from it, you can change the composition over time. We're not going to get into this material today. All right, invite me back in the fall, and maybe we'll talk about how we make the rhyolites. But today, we'll make the basalts. Okay. So here's a couple of pictures of the Big Bend area, some of the rocks in the Big Bend area. This is a basalt. Okay, so this basalt is going to plot over in this area on this diagram from Big Bend. And it's got these little white crystals in there, and those little white crystals are plagioclase feldspar. All right, and this is going to be kind of one of the rocks that we talk about today. On the other end of the spectrum, we have this light-colored rhyolite from the Chisos formation. So the other end of the spectrum is the rhyolite. And these are the rocks we're not going to quite get to today, but you can take and make a rhyolite through some of those processes I very, very briefly went over from a basalt. All right, and so today's going to be talking about basalts. I might point out that in the paper that I was using to help me understand some of these rocks, it describes this rhyolite here as is a light-colored rhyolite with dark 1 to 4 millimeter globule nodules. And that's like the complete description that he gives for this rock. And I'd be willing to bet that many people that have had an introductory geology course could have given a better description than that for this particular rock. It's a pretty weak description of what is actually a very interesting rock. All right. So we'll cut to the chase. We'll put, this is the answers, but yet we're going to figure out how to get to these answers. So here's a number of rocks from Big Bend National Park that are plotted up on that TAS diagram. Okay? And down here we've got some basalts or trachybasalts. Here's our intermediate rocks right here. And then we've got our rhyolites up here. And there's one called a trachyte, which is also quite high in silica. Here's our silica concentration, getting up to 70 or 75 weight%. All right, so this here is really interesting because there are lots of different types of rock in Big Bend, volcanic rocks that is, okay? They range from basalts to trachytes to all the way up here to the, I don't even know what that stuff is, a tephrophonolite, very unusual rock. But there's a large span of compositional rocks in a fairly small area in Big Bend, all right? And this is really kind of interesting. How could we generate so many different compositions from just Big Bend National Park? Well, it all starts down here with the generation of the basalts, okay? And that's what we're going to talk about today. So, basalts are the drivers of magmatism. Some of the questions that we're going to try to answer today, some concepts that we're going to go over, is we're going to talk about the partial melting of the mantle. So I brought in a chunk of the mantle right here, which we can look at in a little bit. Okay, it's not hot still. That's good. All right. We're going to talk about parental or evolved melts. We're not going to spend much time on that, but we'll talk about whether a melt is parental or whether a melt has changed through time. We're going to talk about alkaline compositions and how they form, okay, and what are some of their characteristics. These are really important in Big Bend. They're not so important in a lot of other areas. So that's another thing that makes Big Bend pretty neat, is that they have these alkaline compositions, whereas a lot of places don't. You can go to the Cascade Mountains over in Washington and Oregon. They don't have alkaline compositions, okay? You can go to the Sierra Nevadas in California. They don't have alkaline compositions there either. Lots of volcanic rocks, lots of plutonic rocks, but no alkaline compositions. I can tell you one place they do find alkaline compositions. They find them over there in the East African Rift Valley. I mentioned the word rift earlier today too, so keep that in the back of your mind. So interesting that we have alkaline compositions at Big Bend. Okay. We also have these things called subalkaline compositions at Big Bend. These ones are the ones that are pretty common. We have subalkaline compositions in lots of areas. But the point is, Big Bend has both alkaline and subalkaline compositions. That's pretty cool, and we'll see why. Okay? We're also going to learn some cool terms, or understand a few cool terms. We're going to look at this term lurgilite. So cool, because you got an L and an H. That's the only word I know of like that. Okay? And this here is actually a lurgilite. All right? So it's a chunk of the mantle. We're going to talk a tiny bit about entropy. We're going to investigate this thing called an adiabatic rise. We're going to talk a tiny bit about fractional crystallization. All right? And we're going to talk about what we see in Big Bend and why as well. So got a lot of terms in here. We're going to briefly discuss some of them. Some of them are going to be quite important to our understanding of how we generate these basalts, which are the drivers of our magmatism. Okay. So here is an IUGS diagram. Okay. They like to put lots of names on stuff. But for those that have taken your physical geology, you've heard of the minerals olivine and probably orthopyroxene and clinopyroxene. Okay. So if you have an ultramafic rock, if you have a rock that comes up from the mantle, you can classify it on this diagram. And here's the lurgilite field. So the lurgilite field's got a lot of olivine, but it also has some orthopyroxene and some clinopyroxene. All right? And I'll tell you right now, if we were to start with a mantle that had never been tampered with, before plate tectonics started, our composition would plot right about in the O of lurgilite. All right? So this diagram is to help represent mantle compositions. The rock that I brought in actually plots probably up here someplace.
Where's your mantle rock from?
This is from Kilbourne Hole. So this is from the eastern part of New Mexico. outside of, go north west of El Paso about 40 miles. I'm only 40 miles from El Paso, but it takes about 4 hours to get there apparently. So it's out in some rough and ready country. Actually, this one is from our collection, so this is not my actual rock. But if somebody got it from there, not me. I'll go get my own one of these days. So that's our Rhyolite. So this diagram may appear a bit difficult to decipher, but we'll walk through it together. Is what we have here is we've got temperature across the top, okay, from 0 degrees to 1,000 to 2,000 to 3,000 degrees. That's the centigrade. And then we've got basically depth or pressure coming down. So depth beneath the surface of the Earth. Remember, the crust is quite thin, okay? If we're out in the ocean, the crust is only about 5 kilometers thick, so it would barely even rate on this diagram. Under the continents, the crust might be 50 or 60 kilometers thick in some places, maybe even as much as 80 in a few places. Okay, so the crust would be at the top of this diagram, and we're going down into the mantle to see what the mantle looks like. Okay? If we plot over here in the diagram, this is all solid material. If we plot over here on the diagram, it's all liquid material. If we plot within that red stripe, we've got our solid going from solid to liquid. So we are partially melting as we move from this field to this field. Okay? So the other thing that I'll tell you, we have different minerals that are happy or stable at different depths. At very shallow depths, we have this mineral called plagioclase. It's very stable. It's happy to grow there. Okay? If we go a little bit deeper, we form this mineral called the spinel. And if we go a little bit deeper, we form this mineral called the garnet. And if we go a lot deeper, we get some really cool minerals, which we don't really see at the surface, like ringwoodite and wadsleyite and perovskite. Okay? But we're going to be primarily interested in understanding at what depth we are at. The way we can tell what depth we are at is by looking at what minerals we have in our mantle xenoliths. But there's a problem. We don't have any mantle xenoliths. We don't have any of these from Big Bend. So we have to come up with another way to figure out where, in the depth purposes, we are melting. Okay? We'll come back and revisit this diagram in a moment. So how do we melt? I should back up and not let the cat out of the bag yet. How do we melt the mantle? Anybody have any ideas? You could add heat to it. You could raise the temperature of the mantle, right? That's how you would melt things in the lab. Okay? So if on this diagram we increased our temperature, we would go from the solid area into this purple area, which is a zone of partial melt. Okay? So we can increase the temperature. This does not happen very often. It's very, very difficult to actually do this in the mantle. First of all, where's the heat going to come from? Okay? Maybe near a hot spot like Hawaii you can do a little bit of this. But it's not the primary way in which we generate melts in the mantle. The primary way in which we generate melts in the mantle is this thing called adiabatic rise. Okay? And so what we are doing is the mantle moves around a little bit. Okay? It's like a hard plastic, but it flows very slowly over time. Remember, the asthenosphere is what our plate tectonics runs on. So the asthenosphere is that plastic layer which our plates skid around on, okay? Moving at about the rate that your fingernails grow, a couple centimeters a year. The mantle can move over time. So if we took a chunk of mantle from down here and we just brought it up, okay, slowly over time, we would follow this yellow line called an adiabat. All right? Rocks are very, very, very poor conductors. Okay? Some of you have probably took a blowtorch and a fire brick, and you can hold the fire brick with the blowtorch, right? And you're not going to get burned ever, 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 because the fire brick is a really good insulator. Well, rocks are pretty darn good insulators too. They don't conduct heat well. All right? And so this yellow line shows that if it were a perfect insulator, this yellow line would be straight up. But it's not. It's tilted over just a little bit, right? So as we take this chunk of mantle and we raise it, it loses very little of its heat. Okay? So as it's going up, 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 it loses a little bit. So that line is tilted over just a little bit. It's not perfectly straight.
How many years are you talking about to rise like that?
Well, it'd be quite a long time. I mean, the rise is probably only going about 5 centimeters a year. you know, maybe 3 centimeters a year.
It still can be considered adiabatic?
Yes, work is being done, but we're not actually losing or adding or losing energy. So, but we're doing work on it, okay? Interestingly enough, at some point, we will cross into this purple region. Once we've crossed into this purple region, we've started to actually take what is solid rock and start to melt it a little bit. We have gone from the solid to a place where we're starting to form liquid, okay? We did it all without adding any heat at all. That's pretty cool. We just melted a rock without heat, okay? Now, notice, and I put that black line on there, it's supposed to come in at a later time. There he goes. There's a little kink right there. See how the line's going up, and then there's a little kink. Why do you think there would be a kink in that yellow line once we start to melt it? What's a better conductor of heat? Solid, good old rock or liquid rock? The liquid rock. We can actually then remove the heat from the system a little bit more efficiently. So that bends that line over. Point is, though, we can start to partially melt rocks just by having them come up in through the mantle. Okay? There's a third way in which we can do it, and I may not spend much time on this. How am I doing for time? Oh, I'm getting short already. All right. We can add a flux. Those that have done any type of welding or soldering knows what a flux would be. We can add a flux to our liquid. All right. In this case, we have what they call the dry Solidus. So here we've got a solid on this side and a liquid on this side. So when things are dry, we need a lot of temperature in order to melt them. But if we add water vapor, this is our liquid and solid line. So here's our solid plus water vapor. Here's our liquid plus water vapor. So if we have a dry solid, we need these higher temperatures, and our line looks like that. If we add water vapor or a flux to it, our line will look like this, okay? And this has a lot to do with the entropy or disorder in a system, okay? All entropy is a measurement of disorder. Well, it's a little more than that, but we'll use that definition for today, okay? So crystals, or solids, but especially crystalline structures, are highly ordered. All the atoms in a crystal structure need to be put in there in the proper positions in order for you to have a crystal, okay? Liquids are not very ordered. The molecules are pretty random, so they have a higher degree of disorder. And finally, gases or vapors are incredibly disordered. Okay, the atoms are bouncing around all over the place. They don't know where they're going. It's kind of like ants with the temperature outside. If it's a cold day, the ants aren't too disordered. You get a really hot day and they're just running all over the place. So it's our degree of disorder, okay? This dry curve has a positive slope because as we increase our pressure, so this is pressure on the y-axis, as we increase our pressure, we go from a liquid to a solid, okay? As we increase pressure, we go from liquid to solid. As we increase temperature, we go from solid to liquid, that direction, right? So we have a positive slope. Okay, this is a thermodynamic concept. As we increase pressure, the solid is more stable. As we increase temperature, the liquid is more stable. That's kind of the opposite for if we've got water vapor involved. Over here, if we increase our pressure, our volume actually decreases because we can stick more vapor into a liquid than we ever could stick in a solid, okay? You know, when you're boiling water, you see all the little tiny bubbles forming in there? That's dissolved water vapor inside your liquid, okay? How much vapor do you think is dissolved in the solid? Not much, right? You can't get much vapor pushed into that solid. But you can get a lot of vapor pushed into the liquid. So our volume actually decreases here. But again, as we increase in temperature, we go from a solid to a liquid. So this is really kind of an important concept that once we add liquid, the slope of this line changes dramatically. Okay, so these curves here, you can ignore the detail of them. They're the exact same as this curve here. There's just a whole lot of experiments on them. So we're still trying to melt the mantle. We tried with temperature. Maybe it works, but it's very difficult. We tried with adiabatic rise. That worked well. Now we're trying to do it by adding volatiles. Okay? So here's our diagram up here that we've looked at in a minute ago. This guy here is backwards and upside down, so I fixed it for you. There we go. So this blue line here is our Solidus line. It's that edge of the purple field. Here's our curved geotherm. Okay? Here's our curved yellow dotted geotherm right there. Okay? So now when we add water vapor to some of these melts, we can get very, very close to melting. See that? Okay? And in reality, we actually can melt, but usually only at very shallow depths. All right? So the take-home point would be, we've got 3 ways to melt rocks. We can, in the mantle, we can do it all 3 ways. We can do it by adding heat, but that's difficult. It might happen in a few places like near Hawaii. We can do it by this adiabatic rise. That's actually pretty easy. In fact, we can melt up to around 30% of the mantle that way, maybe 40% in some cases. And yeah, we can make some melt by adding water vapor, but not much. Okay? So in reality, we've got 1 awesome mechanism for doing it, and 2 more that kind of work a little bit. If we ever talk about subduction zones, they actually can melt rocks pretty easily with flux melting. That's a topic for another day. All right. So, forgot to mention, that's the solid and that's the melt. So as we cross that line, we're producing partial melt. All right. So now we have started to partially melt our mantle. Okay? This is good because I know I'm still down in the mantle and you want to be, when are we going to get to Big Bend? We're stuck down in the mantle yet. Because I still have to generate my melts. Okay? They got to come from somewhere, and they come from the mantle. Once I generate my melts, I'll be able to have them rise up into the crust and produce my volcanoes, which is pretty cool. That's why we're here, right? Okay. So once again, at very shallow depths, plagioclase is stable. Slightly deeper, this phase called spinel. And as we get deeper and deeper, this phase called garnet is stable. All right? We're not going to get this deep today. It's too heavy for today's talk. These minerals, they like certain elements. Okay? Certain elements fit into their structure very, very well. If you think about maybe the mineral calcite loves calcium, right? And it also likes a few other things, in that case strontium and a few more. So some of these minerals like things more than other minerals. And if we look here, we can look at a bunch of elements called the rare earth elements. It doesn't really matter which elements we look at, but these ones happen to be convenient for us. All right? So the exact type of element is not necessarily important. But the take-home point is that something called an incompatible element really wants to be in the melt. In other words, it does not want to be in the crystal structure. So given the choice of being in a crystal structure or being in the melt, it will go hang out in the melt. And that's called incompatible. Okay? So when we're melting our rhyolite, we're only going to melt it 5 or 10 or 15 or 20%. Okay? It's called partial melt. Some elements would prefer to be in that melt. Some would be happy as a clam staying in the minerals, staying in the solid. But some are going to go to the melt. So here we see that these heavier rare earth elements, these guys like erbium and lutetium, they want to stay in the rock. These lighter rare earth elements like lanthanum and cerium, they want to go into the melt. So if I'm partially melting this rock, I'm going to have elevated concentrations of these guys. Okay? If I melt this rock 100%, I'm going to be right down here. Everything's going to go into the melt, right? Because it doesn't have a choice then. It has to go into the melt if I melt it 100%. But if I only melt it 10 or 20%, I'm going to preferentially put these lighter elements into the melt. Okay? So at 5% we have a very steep slope, 10% more shallow, 20% fairly shallow. If it was 100%, it'd be a flat line across the bottom. We'll see why this pops up in a moment. Because now, by understanding the chemistry, we can tell what mineral phases were stable in the mantle. Okay. There's one, I'm going to skip ahead on this. There's one special case called Europium. It's called the Europium Anomaly, in which case europium gets sucked out. And I think I'm going to skip ahead on this for the purposes of time for today. But if you have questions about fractional crystallization, stop by and talk to me after the talk today. Okay? So we're back to our now very familiar diagram. There's our plagioclase, there's our spinel, and there's our garnet. Okay? Again, different depths will favor the production of different crystals. And these different crystals will favor different elements. So we'll recap for a moment. The uppermost mantle is made up of rhyolite. There it is. Okay. We can tell how shallow the melt is formed based upon the geochemistry. Okay. If our geochemical curve looks like this, we can tell we have a very small percentage of melt. If our geochemical curve looks like that, we can tell we've got a higher percentage of melt. We never melt the mantle fully. Okay. 3 ways to melt the mantle: increase the temperature, adiabatic rise, or sometimes called decompression melting. It's not a great term, but it's used in the literature a lot. Or we can add volatiles. We really care mostly about adiabatic rise. Okay? So how do we form different basaltic compositions? We'll do that next. Skip back to reality for a moment. We were still in reality, but we were down on the mantle. All right. Now let's get back to the surface. And we've got all these different compositions from Big Bend, including kind of 2 or 3 types of basalt. Okay. We're going to see that we can form these different basalts in different ways. Let's go visit a system that's received a lot of study. So what we like to do in sciences is we like to say, okay, here's a system I don't know much about. Let me go look at a system that's been studied a lot and that might be similar, and that way I can understand better how to apply some ideas to my system. So here's Hawaii. Okay? And in Hawaii, we've got a lot of these rocks called alkaline rocks. So they would plot over here on this diagram. And a lot of these rocks called subalkaline rocks, and they plot over here on the diagram. Okay? And there's kind of this dividing line between them. All right? This has been known for a very long time, that you get alkaline rocks in some places and you get subalkaline rocks in other places. And in a very few places, like Hawaii and Big Bend, you get them both, but they kind of, these ones all hang out over here and these ones all hang out over here. Okay? We'll see why that is in just a moment. Okay? We're going to ignore the details of this. This is called the basalt quadrilateral. We're going to just focus on the base of this pyramid here, which has got forsteritic olivine, enstatite, quartz, albite, and nepheline. Here's nepheline, albite, quartz, enstatite, and forsteritic olivine. All right? And in Hawaii, they were able to plot up these rocks and say, hey, look, all the ones that were in the alkaline field plot over here, and all the ones that were in the subalkaline field plot over here. Okay? Again, they're just looking for differences. Now, these guys by the name of Irving and Barringer, they came up with this dividing line, and it was really pretty critical and pretty good thinking that they came up with this. And they did a lot of work so that we didn't have to. But what they determined was you can't go from one to the other. Okay? You can't go from an alkaline to the subalkaline field, and you can't go from the subalkaline field to the alkaline field. All right? They did this by looking at these things called phase diagrams. Phase diagrams are just like putting greens. Okay? You always, whenever you start the ball rolling, you're going to go to the minimum. All right? So here's the nepheline, albite, quartz phase diagram, which would be the nepheline, albite, quartz part of this diagram right here. Okay? And so temperature is in this direction, would be the y-axis. All right? So if I've got a melt and I start to cool this melt, and let's say my melt is right here and I cool it, I'll hit this slope and come down to this minimum right here. If I start over here and I have a melt and I cool it, I'll hit this slope and I'll come to that minimum right there. It ends up in the same place, right? Same thing over on this side. If I have a melt and I cool it and I hit that slope, it goes to this minimum. And if I have a melt and I cool it, it hits that slope and it goes to the same minimum. But here's the trick. You can't get over this hump. At no point in time, if I ever start cooling a melt from this side, can it ever come over here. Okay? It's called a thermal barrier or thermal divide. Okay? And it's due to the thermodynamics of this system that we cannot take a composition from over here and have it end up on this side. So we cannot take a composition from over here and have it end up over here. It won't happen. Well, this is kind of neat because this gives us two distinct types of basalt now. Okay? And those two distinct types of basalt must be made in different ways. All right? Because you can't make one from the other. Okay, I'm going to skip ahead for fractional crystallization. So, on our Big Bend diagram, we actually have two distinct types of basalt. We've got this dark colored one here, and we've got this yellow one over here. He's in the trachy basalt, but he's pretty darn close. They're pretty similar, but in reality, they are on different sides of this thermal divide. Okay? So if I've got basalts on different sides of that thermal divide, they had to have been made by different processes. So I've got at least two processes making basalts in Big Bend. Okay. So this yellow line shows that dividing line that Irving and Barger came up with back in 1971, and I've just plotted it on our now familiar TAS diagram, or total alkalis over silica. Okay? And the point is, if we make a basalt down here in this field, it can only ever produce these types of rocks along that purple arrow trend. We can't start here and make rocks up here. We cannot get across that thermal divide. Likewise, if I start with basalts over here, I cannot make rocks over here. I have to follow these red arrow trends. Okay? I cannot cross that yellow line, which is a thermal divide. It's like a law almost. I mean, it's thermodynamics, and you can't, you know, it's going to win every time. The lowest energy always wins. So, how can I make different types of basalt? Well, one of the types of basalts that I want to make is this alkaline basalt. So let's back up a moment. Okay, this would be maybe basalts that are made over here, like that one there. Okay? And those alkaline basalts are formed in this purple area. This purple area is reasonably deep in the mantle. Okay? It's 1 to 2 or 3 kilobars, or gigapascals, I'm sorry, which equates to maybe around 50 to 120 or 130 kilometers deep. All right? The other thing that this diagram shows is that we have very small degrees of partial melt. So, alkaline basalts form at very high pressure, but very small degrees of partial melt. Do you remember our partial melt diagram about how we had very small degrees? So these were my heavy rare earth elements, and these were my light rare earth elements. And at very small degrees of partial melt, we had a steep line, and at higher degrees of partial melt, we had a more shallow line. Okay? So at high degrees of partial melt are going to form these alkaline basalts. Tholeiites, which we'll also call our subalkaline rocks, form from either large degrees of partial melt, so more similar to this line on our rare earth element diagram, okay, or very shallow pressures. Now let's put this all together, because we've already talked about the depth of where we're generating our partial melts. Remember, we had our plagioclase, spinel, garnet. That was our depth indicator. We've already talked about the percentage of partial melt adjusting our chemistry. Now let's see if we can put it all together and prove that we've got these two different types of basalt. First let's go back and visit Hawaii. Hawaii is a hot spot. It's hot, okay? And it's also the largest volcano on the face of the planet, right? But over here, in the center is where it's the hottest. So where Hawaii is the hottest, with this giant amount of energy coming up from the core mantle boundary, where it's the hottest, do you think you're going to have a lot of partial melt or a little bit of partial melt? Where it's the hottest, you're going to have a lot of partial melt, okay? Over here on the flanks, away from the center of the heat, away from that influx of heat, you're going to have less partial melt. So if you go to Hawaii and analyze the rocks, and I showed you that diagram where they had both the alkaline and the subalkaline rocks, okay, As volcanism starts in Hawaii, it starts off as alkali basalts or alkalic volcanism. When you get into the main phase of volcanism of Hawaii, it's tholeiitic because you have a greater amount of partial melts. And as volcanism wanes, you go over to Oahu, you're back into the alkali basalts. Some really cool alkali basalts in Oahu. I haven't been there, but I've seen pictures. Okay. So in Hawaii, the percentage of partial melt matches what we think we should get diagrammatically and what we actually get on the surface. This is just another diagram that shows that alkali basalts, okay, form at very small, 5 to 10 degrees partial melt, okay, but very deep, all right, deep pressures, deep within the earth. These tholeiites, which are also known as our subalkaline magmas, they form at more shallow pressures or higher degrees of partial melt. Those that have taken physical geology may have heard this term pickrite, which is lots of degrees of partial melt. Pretty cool rocks, actually. All right. The chemistry, if we look at the chemistry, these rare earth element diagrams from Big Bend National Park, okay, we've got this Alamo Creek basalt. Take a look at the slope on that line there, okay, and then we've got the B Mountain type right here. So from knowing what we've learned earlier in the talk, we know that the steeper slope is a smaller degree of partial melt, and the less steep slope is a smaller degree of partial melt, right? So we will see, I believe, hopefully in the next slide, there it is, that the Alamo Creek, which is this yellow one, is an alkali basalt. And the B Mountain series over here is a subalkaline or tholeiitic basalt. So we'll back up. So the steep Alamo Creek, small degrees of partial melt. The less steep B Mountain, higher degrees of partial melt. Alkaline basalt, subalkaline basalt. Why were the subalkaline versus alkaline important? Because there's our dividing line from Irving and Barger. And thus, there's the Alamo Creek and the B Mountain. And thus, we can only make all these rocks up here from that starting composition. And we can only make these rocks over here from that starting composition. So we must have two distinct basalts. One of them generated by small degrees of partial melt. Okay? And if we were to examine these curves a little more closely, we see there's actually a kink in this one, and that's due to there being garnet in the source. The fact that there's garnet in the source indicates that it must be formed deep, because garnet's only stable very deep, okay? This Europium anomaly is caused if we have plagioclase in the source. So there's plagioclase, which is shallow, and we see plagioclase, boop, dip at Europium. Okay, indicating that B Mountain must have been formed very shallow. So far everything's holding together. The Alamo Creek has a bit of a garnet or deep signature. It also has a very steep curve indicating small degrees of partial melt. The B Mountain has a very shallow curve, and some of them have this Europium anomaly indicating very shallow and higher degrees of partial melt. Two distinct types of basalt form two distinct ways to give us our trends. So I told you a little while ago that another place that we see alkaline basalts is over in the Great African Rift or East African Rift Valley, all right? And I mentioned that maybe way back 700 million years ago, through this very area of Big Bend, we actually had a rifting apart of North America, okay? And so it's actually known as a failed rift in some circles. So some people hypothesize that due to that failed rift, we are still able to generate these alkali basalts when we get some partial melting going on at Big Bend. So the geochemistry that we see at Big Bend is at least in part likely due to a failed rift event that happened 700 million years ago. The Earth's got a really long memory, you know? It remembers, oh, 700 million years ago, I attempted to rift, and so, 670 million years later, I'm going to make an alkali basalt because of it, all right? So there's this inherent structural feature there that allows us to make two different types of basalt. Okay, so we have two mafic types of magma at Big Bend National Park. We've got an alkaline and a subalkaline. Right? They're made distinctly different ways. Again, one is large degrees of partial melt that are shallow. The other one is small degrees of partial melt and probably has garnet in its source, so it's deeper. Once we've made those basalts, they can then evolve to different kinds of rocks. They can, usually by fractional crystallization or other mechanisms, as they evolve to different rocks, but they can never cross that thermal divide line. Okay? Alkali magmas are often formed in rift zones. We can form them, I guess, in hot spots too. We saw them in Hawaii. They are formed in the East African rift zone. Subalkaline, they're pretty common. I told you that to start the talk. Okay, so they're reasonably common. We've got alkaline magmas at Big Bend National Park, and we've got subalkaline magmas at Big Bend National Park, and that's why when we looked at this diagram, we have such an amazing array of chemistries. It's because we were able to make two distinct sets of basalts which have to evolve in different ways because they can't cross that yellow line. You're like, well, why don't we see an amazing array of chemistries at Hawaii? Well, Hawaii is over in the oceanic crust. So the crust is very thin. Oceanic crust is very, very mafic. So if we've got mafic crust and we're starting with mafic rocks, we can't change those compositions much. Hawaii does show two trends. The trend goes from here to here, and the trend goes from here to here. Okay? But over in Big Bend, we're on thick silicic continental crust. So we can alter the chemistries of these basalts quite a bit over time. Okay? And get this really awesome display of different chemistries, which haven't been studied very much. So again, I think I'll end there, and I'll take questions, any and all would be great. I have a few pictures to show as well, so go ahead and ask some questions, and we'll flip through a few pictures.
I'll start off with a question, if you don't mind. About 10 years ago, I was at a conference in Alpine, and the whole session was about the volcanic activity in West Texas, and nobody could put it into a plate tectonic setting, divergent, convergent, mantle can move. So you're suggesting it's actually a divergent plate boundary that's a remnant 700 million years ago?
Yes.
Okay, wow, that's incredible.